Hello everyone. In this video, I want to clarify some terminology when it comes to specifying the position of things in space. This will become handy when we define our own stars and planets. It specifically concerns what we call coordinate system. The most fundamental one is the Cartesian system, which, as we are all familiar with, it has x, y, and z. And then for any particular location, it's just referring to it by traveling x first, traveling y, and traveling z. And on top of that, we have the 3D spherical coordinate. This one is still referring to the same thing, just the way we describe it or the way we measure it is somewhat different. So for the same x, y, z point, we can measure it by measuring this angle and this angle and this distance r. That is essentially the 3D spherical coordinate system. And then when we apply that onto Earth, because the radius of Earth, if we assume it doesn't change, then only two numbers suffice to describe the position of things. That is lambda and phi, which is the latitude and longitude. When we go to space, we talk about orbits. And when we talk about orbits, one particular concept becomes very useful, which is called inclination. In order to describe this, we need to first define something that is called a plane of reference. Once we have a plane of reference, then for any object we are looking at, and if that object creates another plane, in which case it's the orbit, then we can measure this inclination. This one is a generic term which I always confuse with things like declination and those other coordinate system specific term. But in general, this is just a general term measuring this angle, the orbit from the plane of reference. Then if we go to something called celestial sphere, this one, the most important one here is the celestial sphere refers to this kind of sphere, and it can actually apply to any object. So you can talk about the celestial sphere with Earth centered in it. You can also talk about celestial sphere with Sun centered in it. The important part is the few characteristics of a celestial sphere include the North Pole and the South Pole. And typically when you define the celestial sphere centered around Earth, the North Pole matches our North Pole, the South Pole matches our South Pole. And then you have your plane of reference, in which case is the equator, the plane described by the equator. And in that case, it's called celestial equator. Again, as I was saying, you can define a celestial sphere centered around the sun. In that case, the plane of reference will not be the equator of our Earth. And then from there, we have the few concepts called right ascension and declination. Now, right ascension is just like the spherical coordinate in terms of phi, and declination is just like theta, except in the case of celestial sphere, we are measuring right ascension from a point called equinox. The equinox can be defined arbitrarily. It's just the starting point, which you call degree 0, and then there's a 360 degrees. And then the declination, to be honest, I'm not sure exactly which direction it goes, but looks like it's opposite to the 3D spherical coordinate. So it goes something from here instead of here. Okay, so those are the two terms that is most important. Now in this particular image, it's also highlighting this ecliptic, although I will talk about it in the next page, but basically this one is referring to the orbit of the Earth relative to our greater sun somewhere here. So if we treat that as a reference plane, that is the meaning of ecliptic. Now we have quite a few coordinate systems that are interesting. The first one called equatorial, because the term equatorial is very similar to equator, so that one is actually referring to our Earth, using Earth as a center and using Earth as the reference plane, and then we have something called the celestial equator, which is the celestial sphere centered around Earth, using equator as the celestial equator and as our reference plane. From there, we have the sum of the terms called declination, right ascension, as I was saying, just the spherical coordinate measured in a different way. And then we have the ecliptic coordinate system. In this particular case, the ecliptic coordinate system is referring to the Earth's orbit. So to illustrate this better, we can go to Celestia. Now here you can see we have selected Earth right here, right? So if we zoom out, you can see there is this coordinate, there is this orbit. Within the solar system, there are many orbits, and especially if you look at the comets, you can see it's a 3D structure, and they all have slightly different angles, right? And so when we talk about ecliptic reference system, we are always referring to the Earth's orbit as the plane of reference. So when we talk about, say, the inclination of Mars relative to Earth, we are talking about the angle from Mars orbit relative to Earth's orbit, in which case it's the ecliptic plane. So here we can have ecliptic latitude, ecliptic longitude, and that's again referring to the orbit of Earth. So that's pretty much it. And once you can figure out those ones, I guess it will make a whole bunch of sense. The only thing that really make me confused is the inclination, which is, it's just referring to the tilt between two different reference planes. Again, you can just think of this particular image. It's not specific to either the equatorial coordinate system or ecliptic coordinate system. There's another plane that might come into play when you are in the space, and here I'm illustrating it in Blender. You can see we have a galaxy here, right? The galaxy itself will have a plane. If you draw a rough plane, that's the galaxy's plane. We can call it galactic plane. And then inside the galaxy, we have our sun. Here, let me just jump to my sun. That is our sun, right? So our sun will have a whole bunch of things orbiting around it. It will have some general plane, and that plane, in this case, is like this black thing you are seeing right here. If we actually give it a little bit of color, it's more obvious, right? So that is a huge plane of all things orbiting around the sun. That one has a name. That one has a name, actually. It's called the what's the thing? Invariant plane. Okay, that is called invariant plane. On the other hand, we also have a plane, which in this case is drawn as the same one, but we also have a plane as shown in Celestia based on Earth's orbit. That is what we call the ecliptic plane. Notice it's not going to be the same as the invariant plane because there are lots of orbits. If you average, then you get the invariant plane, right? So from the ecliptic plane, we can then have something else, which is the Earth itself will have its own small plane, which is an equatorial plane, and which defines our equatorial coordinate system and also our celestial sphere, right? So that is the plane based on Earth's equator. So I hope this one clarifies things a little bit, and thank you for watching.